All right. Well, on Wednesday, we introduced the Bootstrap, and we kind of we did, we resampled our values with replacement, and we said, when you do this, you can simulate the sampling distribution if the null hypothesis were true, and yeah, that's what we did. We said we do. We use Bootstrap in situations where our data was obtained via random sampling, and that the assumption we are making is that we can kind of duplicate the sample that we have many times and have that stand in for the population, and thus we will we can simulate our sampling distribution. Today we're going to look at Bootstrap some more, but this time we are going to use the library boot. So within with R, there is a library called boot, or a package called boot, and it's pretty useful. It has some additional utilities, and there are other functions or other libraries built around boot that take the results of boot and kind of give some useful information with it. So the primary function that that package boot provides is boot, and it can be used to perform both non-parametric and parametric bootstrap. Today we'll look mostly just at non-parametric bootstrap here, so that's what we'll do. So you just load it up by calling library boot. If you don't have it already installed on your computer, you can do install.packages boot, but that's how it works. Okay, this is just the straight up description or help file that pops up when you call help on boot, and it says this is what the function does. It says generate R bootstrap replicates of a statistic applied to data. Both parametric and non-parametric resampling are possible. For non-parametric bootstrap, it says the possible resampling methods are the ordinary bootstrap, balanced bootstrap, et cetera, et cetera, et cetera. And for non-parametric ones, it can do all kinds of other stuff. And basically, when you look at the definition of the function, or not the definition, but the kind of the how you're supposed to call the function, it says there are a bunch of arguments that you could provide to the function, but it's really just the first three: data, statistic, and R, that don't have default values. The rest all have default values. Okay, so you have sim, ordinary, S type equals this, and strata equals this, and all sorts of other stuff that we're not going to worry about today. But really, it's just these three that you have to provide every time you call boot. So we'll take a look at those three arguments. So number one is the data as a vector, matrix, or data frame. If it's a matrix or data frame, then Bootstrap will consider each row as an observation, and it will resample the rows. The statistic is a function that's going to calculate a statistic that when applied to some vector will returns a vector containing the statistic of interest. Okay, either just a single value, you can have it return multiple values, but it'll return the value of interest that we are trying to test. So it could return something as simple as the mean of your data. It could be something like the 10th observation, a difference between two means, or something like that. Okay. The statistic function takes in two arguments: the data and a vector of indices, and we'll talk about how this statistic function works. And then the last value that you need to provide when you call boot is the number of replicates. Some number like 5,000, 10,000, or maybe something else, some integer value for how many replicates he needs. Okay, so again, the function boot requires we provide it 3 arguments: the data that will be resampled, the statistic to be calculated, which is a function that we will define ourselves, and the number of replicates R. Okay, you can specify other arguments, but they all have default values associated with them. So if you don't specify them, the function will still run. And the way Bootstrap, or the way the function boot performs Bootstrap resampling is rather quite clever in that rather than sampling the actual values, what it will do is it just resamples the indexes, and it resamples only the indices of the values. And so what I'm going to show you is just kind of how this works and what it's doing. And when you resample the indices and you subset the data using the resampled indices, it's equivalent to just resampling the data directly, resampling the data itself directly. So just for the purpose of illustration, we're going to pretend that our population are the 26 letters of the alphabet. Okay, so our population is the 26 letters of the alphabet. We're going to sample with replacement, and so we can just kind of see what kind of values we get. And so here I'm going to do set seed 5, and I'm going to just sample 10 values from the population directly with replacement. And when I do this, I get the letters B, K, Y, O, K, Y, I, U, G, W. And so just by coincidence, I get K and Y. Both of those values got selected twice. And that was, oops, just drop something over here. So that could happen if you, so these are the results we get if we resample our values from the population directly. An alternative that we can do, and this is how Bootstrap library boot is going to work, is that it is going to take the values 1 through 26. It's going to take the values 1 through 26 with an integer corresponding to each value in the population. And here we're going to sample the values, the numbers 1 through 26. We're going to just select 10 of them with replacement. And if I use the same seed, set seed 5, and I do sample the numbers 1 through 26, I want 10 of these things with replacement, I'm going to get back these values: 2, 11, 25, 15, 11, 25, 9, 21, 7, and 23. And then what I'm going to do is I'm going to take the population, which is my alphabet, A through Z, and we're going to subset it using these indices that I've resampled. So the second letter in the alphabet is B, the 11th letter is K, 25th letter is Y, 15th is O, 11 is K, 25 is Y, 9 is I, and so on and so forth. And we can see that when I subset the letters A through Z using these indices that I've resampled, I get the exact same results. I get B, K, Y, O, K, Y, I, U, G, W, which is exactly what I had up here, B, K, Y, O, K, Y, I, U, G, W. So resampling just the numbers 1 through 26, or resampling the indices themselves, is equivalent to resampling the original values directly. And here it's just a matter of taking those values and then subsetting the population based on those indices. Okay, so let's work through an example and take a look at how we can use library boot and Bootstrap resampling on a data set like the iris data. Okay, so the iris data set, it's a very popular data set. I think I've spoken about this, maybe not, but basically there were 150 observations. There are 150 observations, 50 from 3 different species: Setosa, versicolor, and virginica. And the researchers had measured the sepal length, sepal width, petal length, and petal width of 50 specimens of each of these species. Okay, and so just so you can kind of see, this is a picture of an iris, and the part down here, this is the sepal, and then the part that stands up, this is the petal. Okay, So the petals or the standards are kind of upright, and then the parts that fall down, those are known as your sepals. And so here's kind of for an iris, this is the falls, those are the sepals. The standards are the petals are the ones that are kind of standing a little bit more upright. And this is the diagram that kind of says this is what a versicolor iris looks like. And so we're measuring the length and width of the sepal. And here's setosa and here's virginica, and we're measuring kind of the length and width of these different things. But I don't know, this is, see, I don't know, these are kind of conflicting, right? This thing, they're labeling this one says tosa versus color virginica. I don't know if people know anything about irises. We're all just statisticians making stuff up here. But anyway, we've got some information there. All right. And so anyway, we've got measures like 5.1, 3.5, 1.4, 0.2. And you know, what kind of values do we get? So here, just to look at some summary statistics, I used dplyr, and I said, you know what, I want to know the mean and standard deviation of all 8 of those, of all 4 of those variables. So I want the mean sepal length, standard deviation of sepal length, mean sepal width, standard deviation of sepal width, so on and so forth, mean and standard deviation for all 4 variables. And I want it split out by each species. So we're going to group by species. And so I get kind of 24 of these summary statistics. And what we're and here's a plot of all 4 variables, kind of pairs plot. The setosa appears in red, versicolor in green, and virginica in blue. And we can see, yeah, you know what, we can distinguish the flowers from each other kind of by where they're located here. All right, what we want to look at, let's say we want to do a hypothesis test and we want to compare the sepal length and flowers from setosa versus versicolor. Okay, so if we look at sepal length for setosa, I got 5.01. The sepal length for versicolor is 5.94. Here, we're just going to keep it simple. We're going to just look at these 2 groups only. So we're going to ignore virginica. Setosa is 5.01, mean sepal length. Versicolor, the mean sepal length is 5.94. Could that be a result of randomness? Well, let's take a look. So if we look at sepal length, which appears like this, so we see, yeah, the mean sepal length of setosa in red is right around 5. And then if we look at the green group, the mean sepal length for the green dots is right around 6. Okay. And, you know, there's some overlap, but, you know, could the means be the same? Well, according to this t-test, the answer is no. Or we've got strong evidence that they are not coming from the same population. So the t-test here says iris $sepal.length 1 through 50 versus iris $sepal .length 51 through 100. The first 50 values in sepal length correspond to setosa. The next 50 values correspond to versicolor. So here we're asking, is the mean of the setosa sepal length, which is the first 50 sepal length values, is that the same as the mean sepal length for versicolor? Okay, and the answer, so we're going to compare the first 50 versus the mean of the next 50, and we get a different, we get a p-value of practically 0, 2.2 times 10 to the negative 16. So this is about as close to 0 as we can get, and we get a t of negative 10. Okay, so we're like 10 standard errors away from 0. So that's quite a significant difference. And again, you know, the mean of x 5.006 versus the mean of y 5.936, we're getting a difference of 0.93. Okay, a difference of 0.93, and it says, you know what, it doesn't seem like we could get this difference from random chance. So that's kind of your classic t-test. So let's try doing a bootstrap. Let's try doing bootstrap. And so here, I'm going to do bootstrap by resampling the values directly. I'm going to take those, the sepal length values, and we're going to say this is my population, and I'm going to resample the values directly. And so what I'm going to do here, okay, so I'm going to do 10,000 repetitions. So I'm going to repeat this 10,000 times. And what I'm doing is I'm going to put all 100 values into the same group, because we are creating the sampling distribution if under the null hypothesis. If the null hypothesis were true, we're saying the values for setosa and the values for versicolor, they have the same mean, or effectively that they're coming from the same population. That's what the null hypothesis is stating. The null hypothesis is stating that they're basically in the same population, and that any difference we're observing is just a result of random chance. That's what the null hypothesis is stating. So here I'm going to put sepal length, all 100 values, into what we call the bootstrap population. And then what I'm going to do is I'm going to just randomly sample 50 values from the bootstrap population and throw them into group A. And we're going to select 50 values from that bootstrap population and throw them into group B. And we're going to say, okay, if they're all coming from the same population, could I get two groups where 50 of them are in group A and 50 are in group B? And is it possible for the means of the two groups to have a difference of, 0.93, which is the difference that I got between the setosa average and the versicolor average. And so I do this 10,000 times, each time just selecting 50 values from that population, throwing me into group A, 50 values from the population and throwing them into group B. And we get a difference, most of the time we get a difference of 0. And the very largest difference I got was 0.552. So not once did I get a difference of 0.93. Okay, the most negative difference I got was 0.47, negative 0.47. Not once did I get a difference of negative 0.93 or something larger. So it doesn't seem very likely at this point. Before I forget, let me go ahead and give you your first view quiz answer, which is the letter E. E is your first view quiz answer. E. Okay. All right, so this here, I am just going to the bootstrap population and I'm selecting 50 values directly. All right, and maybe I'll just pause here for a moment and just make sure that it makes sense that for the population, we're putting all 100 values together. And then I'm resampling 50 values with replacement from the population. So I hope that makes sense. I can't see your faces, so I hope. Okay, all right, thanks for your thumbs up. I appreciate that. All right, so let's contrast this and say, well, what would this look like if rather than resampling the values directly, what if I resampled the indexes and subset? So if I resampled the indices and I subset based on those resampled indices, what would this look like? So here, rather than resampling the values directly, I'm going to take the values 1 through 100, because that's how many values I have in my data set or in my population. We're going to take the values 1 through 100. We're going to sample those values 1 through 100 with replacement. We're going to sample those values 1 through 100 with replacement. And this is going to form my resampled indices. From there, I'm going to subset the iris data set using those resampled indices. So I'm going to say subset iris using the resampled indices. That's going to form my resampled data. And now that I've resampled my data, I'm going to put the first 50 into group A and then the next 50 into group B. Okay, so again, this data is all kind of shuffled up now. Now that I've resampled my data, because the indices have been shuffled up and resampled, the data, this resampled data itself is all shuffled up. And now I'm taking the first 50, putting them into group A, and then the second 50 and putting them into group B. So we're going to say, what's the difference between the mean of group A and the mean of group B? We do this 10,000 times, and we say, well, what kind of difference do we get? Most of the time, again, we're getting differences of 0. The largest difference I got was 0.552. The most negative difference I got was negative 0.47. And even though it feels a little bit different, we're actually getting the exact same results. Okay, these results are exactly the same. We can say, are all of these values for the differences equal? All 10,000 values are exactly the same, which feels a tiny bit strange, but we're getting the same results. Here I called the function sample one time, asking for 100 of these values. Over here, I'm calling the function sample, I called it twice, okay? But doing calling sample, asking for 50 values, and calling sample and asking for 50 values produces the same results as calling sample and asking for 100 values when you're doing it with replacement here. So here we resample the indices, and once we got those indices, we subset our data. We're going to put 50 into group A, 50 into group B, and we're going to calculate those differences. So these are going to kind of give us the values that we can get here. All right. So if we understand how this works, resampling the indices, and then subsetting our data using these resampled values, then we can write a function that will be used by Bootstrap, by Boot. Okay. So in order to use Boot from library Boot, we have to write this function. Okay. We write a function called the statistic function, and this function takes in 2 arguments, the data and the indices. The Boot function will resample the indices itself. It's going to resample the indices itself. It's going to pass those resampled indices to the statistic function, and then the statistic function will then return the calculated value. Okay, so in this case, we want to calculate the difference between the mean sepal length of 50 setosa flowers versus the mean sepal length of 50 versicolor flowers. So this is what our function is going to look like. Okay, so here's the function that we would write. And if you compare the lines of code here versus the lines of code I've written here, look at these lines. Resampled data is iris square bracket resampled indices, comma, group A is this, the first 50 values, group B is this, the resampled data sepal length, the next 50 values, calculated the difference between group A and group B. Those lines are pretty much exactly the same. It's just I've taken, here I'm not doing, there's no call for sample anywhere in here. All I'm doing is I'm going to take the data and I'm going to subset on the index. The function boot is going to pass random index values here anyway. And so that will form our resampled data. So the index values that it's going to pass, that function boot is going to pass, will form our, will be random. And so when I subset data on that, we'll have our resampled data. And then I'm going to take the first 50 values, throw them into group A. I'm going to take the next 50 values and throw them into group B. And I'm going to take the difference between the mean of group A and the mean of group B, right? And then this will be our difference, and we're going to return the difference. Technically, I don't need to store it into difference just to return the difference. I could have just returned mean of group A minus mean of group B, but you know, for readability, this is what I've done. Okay, is that all right? How this function is being written? It takes in 2 arguments, the data and the index, and it's going to subset the subset our data using the resampled index. Okay, so to get this to work, we call boot. The data that we're interested in is the first 100 rows of the iris data set, because we're only just comparing setosa versus versicolor. We're only looking at those two species, so just the first 100 rows. The statistic that we want to calculate is going to be determined by this difference function that we've written here. So this difference function, these differences That's the statistic we're going to be calculating. And then we're going to ask for 10,000 replications. So this is what we do. We're going to run this. We're going to store all of the results in boot_results. I'm going to give you your second view quiz answer. Second view quiz answer is C. C as in cat. C as in cat. Okay, and so this is the result of calling boot. So here, if we look, inspect boot_results, we get back a long list. We get a T0, we get a T. A T has 10,000 values. R says we did 10,000 replicates. It also contains the data frame. We said we're looking at the first 100 values. And so we have 100 observations of 5 variables, the 4 variables plus the species. Okay, and then it got other information that that came back when it created the results. The Bootstrap results are stored in this matrix $T. So within the list boot results $T, there's a matrix, 1,000 rows, 1 column, and if this function, if the difference function returned a vector with multiple values, then you get a matrix with multiple columns. But here we just have a vector or a matrix with 1 column, and those values say, you know, when I did one bootstrap resample, I got a difference of -0.092. Another bootstrap resample, I got a difference of -0.348. Another bootstrap resample, I got a difference of -0.146, et cetera, et cetera. So we can see, you know, what kind of values do we get? Most of the time we got values around 0. Now these values aren't exactly the same as the bootstrap results that we got when we did it manually, and that's because, excuse me, the way Bootstrap does its random sampling is just ever so slightly from calling a naive call to sample, but it still does sampling with replacement. So how can we calculate the p-value? Okay, so our p-value is going to be how often did we get a difference as large as ours or something more extreme in the sampling distribution if the null hypothesis were true. That the observed difference is stored in this value $T0. Okay, so $T0 -0.93 is the result of if, when you call the difference function, if you didn't do any resampling. Okay, so normally index is going to be a jumbled mess. We sampled the values 1 through 100 times with replacement, so you get, you know, some mix, you know, 58, 72, 3, 17, 85. Okay, 100 of these shuffled values. Okay, but T0 is what you would get if you just passed the vector 1 through 100. So no shuffling, just what if you took the original data, you put the first 50 values into group A and the next 50 values into group B. Well, group A would then be the mean setosa, and group B would then be versicolor. Because if you didn't do any shuffling, the first 50 are all setosa, and then the second 50 are all versicolor. And so if you did no reshuffling, what kind of difference would you get? You would get a difference of -0.93, basically the difference of setosa versus the difference of versicolor. And that's what we're getting here, okay? We get a difference of -0.93. If we looked at the summary table, which we had way back here, and we said, okay, well, what is the mean for setosa and the mean for versicolor, 5.01 versus 5.94, you know, 5.006 versus 5.936, we get a difference of 0.93, okay, or -0.93. So the results here is -0.93. You could also just call T0. T0 again is if you did no reshuffling, just past the index 1 through 100, what kind of difference would you get? You would get a difference of 0.93. And so we said, well, okay, after 10,000 repetitions, did we ever get a value in boot results $T that was greater than or equal to the absolute value of 0.93? And the answer is no. This happened 0 times. The largest difference we ever encountered was 5.06. The most negative difference we ever encountered was negative 0.434. Neither of those have an absolute value greater than 0.93. So after 10,000 repetitions, we never saw a difference of 0.93 by random chance. We never, that kind of difference just never happened. And that aligns with what the t-test says. The t-test says, you know, what's the probability of getting this difference of 0.93 by random chance? The probability that that would happen is on the order of 10 to the negative 16, or something very close to 0, practically 0, in a practical sense of 0. So that aligns. After 10,000 repetitions, this happens 0 times. There's a few functions when you use library boot. You can just call plot. You can call plot on your boot results, and you get this histogram and QQ norm. So this is the histogram of all of the differences that we observed. So when you look at T, this is the histogram you get. So when we shuffled the data and we resampled them, most of the time we got differences right around 0, centered around 0. Okay. Sometimes they were a little higher and sometimes a little bit lower, but it seems like the most extreme value we got was something like positive 0.5 or negative. We didn't even quite reach negative 0.45, but those are kind of like the most extreme values, where most of the values are, it looks like it's between negative 0.2 and positive 0.2. Okay, the broad majority are between there and there. This dotted line over here is our T0, the test statistic, or the statistic we got if we didn't do any reshuffling. So if we did no resampling and we took the difference of Setosa versus versicolor, we got a difference of negative 0.93. And what we can see here is that this kind of difference is almost never going to happen from random sampling. So when we look at random sampling, we got this kind of difference almost never. So that would be a strong indication to us that the difference we observed of 0.93 is not because of random sampling. Here is a QQ norm, and we can see that this histogram indeed looks like the normal distribution, which is what we would expect because we have a large sample and we're calculating the mean, right? If we had something, if we were calculating different test statistic, this histogram T might not have a normal shape, and this plot here might not, might indicate that it's not normal. If we wanted to just kind of look at the sampling distribution, and sorry, this the plot here got, the bottom part of the plot got cut off. We can just say, hey, let's look at, create a density plot of the Bootstrap results, and it would be centered right here on the x-axis. It would show 0. But the sampling distribution here, estimated sampling distribution, looks pretty normal, centered right at 0. You can also create confidence intervals. So there is a function called boot.ci, and this will create confidence intervals based on the Bootstrap results that we have. There's a little bit more information about this on data camp, okay? And so here, this is talks about a little bit more about using Bootstrap, using R, and so they also do it using the iris data frame. Okay, here they're doing it on let's see, the function that they're writing is going to calculate the looking at the correlation along with the median median of let's see, of kind of the first 2 variables. Okay, so they're doing something a little bit different, but so their thing calculates multiple things, and anyway, at the end you can create a Bootstrap confidence interval, and you get it produces 4 of these things: the normal confidence interval, the basic confidence interval, the percentile confidence interval, and the BCA, I think, bias corrected accelerated or something. And well, I have an explanation later about the the different confidence intervals that it will produce. Okay. Now, one problem though is for our results, because our not once did we get a value that's more extreme. We have a p-value of 0. And so with a p-value of 0, we have no bootstrap variances that we can apply. And so because our empirical p-value is 0, it gives us an error with the boot.ci. Okay, but we'll look at another example where we are able to do this. Okay, so the advantage of using library boot is that, we've got functions and libraries that take out advantage of the output of boot, and we can perform bootstrap for other more complicated statistics if we need to. So there's some nice things about using boot. There's a lot of kind of a rich library out there of things that use the results of library boot. Okay, so here's just a different example. Let's say we wanted to do a bootstrap study on the correlation between sepal length and sepal width for all of the species in the iris data set. Okay, so if we're going to look at all of the species in the iris data set, we can say, is there a correlation between sepal length and sepal width? And so looking at all of the data points, the correlation is not very strong. We actually get negative correlation, negative 0.117, okay? So close to 0 and actually negative, which is strange. Sepal length and sepal width, you'd think there would be a positive correlation, or I don't know, bigger petals, longer petals would probably be wider petals and something like that. And this is an example of Simpson's paradox. Okay, Simpson's paradox. If you look specifically at just one species, Setosa, okay, we see positive correlation. As the sepals get wider, the length gets longer. Okay, there's positive correlation between length and width for Setosa. If you look at the green dots, there's also positive correlation. If you look at the blue dots, there's positive correlation. So when you look at the species individually, there's positive correlation. There's positive correlation between the length and the width for individual species. But when you look at all of the species together, you end up getting negative correlation, which is kind of a strange thing to think about. But that seems to be what's happening here. Okay, let's take a look at what we can do here. So the correlation between length and width, we end up getting negative 0.117. What we have to do is we have to create a function to use with Bootstrap, right? So to use Bootstrap, we need to provide the data set. We're going to look at the full data set, iris data set, 150 values. We're going to use this function that we're going to write. We're going to calculate the correlation. And the correlation function needs to take in 2 arguments, data and indices. Data and indices. The data will be the full iris data set this time. And the indices will be the values 1 through 150, but just randomized. Randomized 1 through 150. And we're going to say, well, what kind of correlation can I get? Okay, so we're going to just take the first column and the second column of our resampled data set, calculate the correlation, and return that. We're going to just see what kind of variation can I get from the correlation. Do I ever get a positive correlation? So here's what I get, and so most of the time I get a correlation centered right around our sample average, which makes sense because we're using the full data set here. So in the full data set, I have a correlation of negative 0.117, and whenever I resample, I'm getting correlation right around there. And now we can create a confidence interval. We can create confidence intervals for the correlation, and we have a normal confidence interval, basic confidence interval, percentile confidence interval, and a BCA confidence interval. All of these confidence intervals go from negative to positive, indicating that for our 95% confidence interval, 0 is a plausible value for the correlation. 0 is a plausible value for the correlation. So we're not, it's hard to say. But And so here's just kind of a quick rundown of some of these 4 different confidence intervals. The normal confidence interval uses the normal distribution. It uses 1.96 times the estimated standard error. Standard error is estimated from our Bootstrap results. You have the percentile confidence interval, which will just kind of take the 2.5th percentile and the 97.5th percentile. So basically it sorts them and it gives you basically, if you have 10,000 results, it'll give you the 250th result versus the 9,750th result, throwing away basically the most extreme outcomes to kind of give you a sense of the confidence interval. And then you have the basic confidence interval and the bias corrected accelerated interval, which I don't really know what that is, but you can read about it. I think here's the article, Bootstrap Confidence Interval by Brad Efron, to talk about what exactly the thing is, and you can read this article here. But anyway, that is using library boot to perform Bootstrap in R. It's a handy library. Again, a lot of kind of other packages and functions and libraries have been written that take advantage of the output format of Bootstrap, right? So it's expecting data kind of in this form, and it can produce all of plots and confidence intervals and other features from this. But that's it. That's all I've got for you guys today. Let's go ahead and end. Let me give you your last view quiz lecture today, which is the letter B. B as in bear is your final view quiz answer for today. We'll end here. Have a good weekend, and we will see you next week. See you Monday. Have a good rest of your day.